Hi, hello, and welcome to another amazing session on electromagnetic field theory and waves. In today's session, we'll see a brief introduction of the magnetostatics, the magnetic field intensity, magnetic flux density, the magnetic lines of force or the flux lines, and the relationship between the magnetic field intensity and magnetic flux density. So let's get started. So in electrostatics we have the electric field. So electric field exists only for a positive charge or only for a negative charge. So if we consider a positive charge, the electric field lines start from the positive charge and they terminate at infinity. You can see the direction of the arrows here. These are the electric field lines or the electric flux lines. And if we take a negative charge, the electric flux lines, they start at infinity and terminate on the negative charge. Whereas in magnetostatics, the moving charges, they produce the magnetic field, and stationary charges do not produce magnetic field. So in magnetostatics, moving charge particles or stationary charge particles produce the magnetic fields. So this scientist Oersted, he discovered a relationship between the electric fields and the magnetic fields. He discovered that when the charges are in motion, there is a presence of some magnetic field and electric current also, and if the current flow is steady, we call it as a steady magnetic field. And this study of the steady magnetic field, which is due to the flow of direct current through the conductor, it is known as the magnetostatics. So we'll see some of the properties of the magnetic field. You can see a magnet here which is having a north pole and a south pole. So any permanent magnet, it has two poles, one is the north pole and the south pole, and the region around the magnet where the influence of the magnet can be experienced, we call it as the magnetic field. So if whether the magnetic field is present or not, that can be known by using a compass. Just you bring a compass closer to a magnet, then it will show the direction of negative and north and south poles. So the presence of the magnetic field can be known by using a compass. The magnetic field can be represented by imaginary lines around a magnet. So these are known as the magnetic lines of force or magnetic flux lines. So always the magnetic flux lines, they start from the north pole and they terminate on the south pole. And also the magnetic flux lines exist in pairs only. That means we need to have the both north and south poles for the magnetic field or the magnetic flux lines to be present. Whereas if you take the electrostatics, if only a single positive charge or if there is only a single negative charge also, there will be presence of the electric lines of force or the electric flux lines. But in the case of magnetostatics, the magnetic flux lines for the magnetic flux lines to exist, we need to have both north pole as well as the south pole. So this is the meaning of this property. The magnetic flux lines exist in pairs only. So here the pair refers to the north pole and the south pole, not only a single north pole or a single south pole. This is the right hand thumb rule. You can see the diagram. If you hold your thumb, fold your fingers in this manner and point the direction of the thumb along the conductor which is carrying a direct current of I. So in such case, the curling of your fingers, that gives the direction of the magnetic field. So this is known as the right hand thumb rule. by using the right hand thumb rule, we can find the direction of the magnetic flux lines or the magnetic field, and the direction of current also can be known. So magnetic field intensity. This is defined as the force experienced by a unit north pole of 1 Weber strength. So units are newtons per Weber or amperes per meter. So this is a standard unit for magnetic field intensity, amperes per meter. So magnetic flux density. The total number of magnetic lines of force which are crossing a unit area in a plane at right angles to the direction of flux. This is known as the magnetic flux density. It is denoted by the letter B, and the units of the magnetic flux density are Webers per meter square or Tesla. So this magnetic flux density, it is similar to the electric flux density D in electrostatics. So the permeability of free space, we write it as mu naught, which is equal to 4 pi into 10 raised to minus 7 Henry per meter. For any other medium, the relative permeability is mu r. So mu is equal to mu naught into mu r. For non-magnetic media, we write mu r is equal to 1, and for any other media, mu r is greater than 1. So here we have a relationship between the magnetic field intensity and the magnetic flux density. So in electrostatics, there is a relationship between the electric field intensity E and the electric flux density D. So they are related through a permittivity epsilon. So D is equal to epsilon into E, where epsilon is the product of epsilon naught and epsilon r. So we have a similar equation in magnetostatics between the relationship between the magnetic field intensity and the magnetic flux density B. So we can write B is equal to mu into H, where mu is the product of mu naught and mu r. Mu naught is the permeability of free space and mu r is the relative permeability. So these terms are similar to the terms used in electrostatics, where epsilon naught is the absolute permittivity and epsilon r is the relative permittivity. So this is the relationship between magnetic flux density and the magnetic field intensity. So that's it in this session. Thank you.